And interestingly, there's been already a lot of inspiration in the design of current deep learning coming from living intelligence. So of course, the neural nets themselves come from neuroscience, but things like the idea of a distributed representation, the fact that a concept is not represented by a single unit, but by a pattern of activation, for example, comes from observing what we see in the brain. The architecture of convolutional nets comes from observing the visual cortex. The kind of nonlinearity that we're using in neural nets, the ReLUs, for example, which really came from neuroscience, and we tested in neural nets in around 2010, really is something people usually don't know, but really comes from neuroscience. The idea of spikes, we haven't yet completely integrated that, but actually we have things in deep learning that are really much inspired from spikes, like dropout, where you introduce noise that shuts off some of the units randomly, or the work that's been done in quantizing the activity of neurons in order to reduce energy, again, something that brains have to deal with, and many other aspects. So now let's talk about the state of deep learning so that we can get into our subject of high-level cognition. We've made huge progress, much more than even my friends and I expected a few years ago, but it's in some areas of cognition, of intelligence. It's mostly about perception, things like computer vision, speech recognition, and synthesis. Some things in natural processing we're doing well, but we're still far from human capabilities and that domain. Playing games, of course, like the game of Go. And then, you know, with all the success we've had, some people think that, well, we're done. Right? We just need to scale things up. If we just have larger data sets, bigger models, faster chips, we're going to build intelligent machines with the kind of algorithms we already have. I don't think so. I think there are actually many pieces in the puzzle that are missing. And that's the kind of thing I want to be brainstorming about with you. So why do I think so? So there are some fundamental ways in which I think we are lacking. In terms of the symptoms of this, we can see that what we call sample complexity is not good. So the number of examples that you need with a machine learning system to learn a new task is, for now, much higher, much worse than what, say, a human needs. So of course, there's no magic here. Like, humans are able to learn a new task quickly from very few examples because they already know so many other things that they've learned previously. And so if we're going to solve this problem in machines, it's going to be the same thing. We're going to build machines that know a lot of things about the world, and then when they're presented with a new task, and maybe just a few examples of it, they'll be able to do as well as humans eventually. Another aspect is that if you look at the state-of-the-art systems, the industrial systems that are deployed out there, they use humans in very important ways to help define what are the high-level concepts that the machine is supposed to know about. So when we label images and we say this is a cat, this is a dog, this is a chair, it's the human who decides what the high-level concepts are. And then the machine learns to map the raw data like pixels into these high-level concepts. But babies, for example, are able to figure out lots of things in a completely autonomous way. Even things that they figure out that their parents don't tell them anything about. So for example, babies figure out how physics works. Like, they understand gravity, they understand pressure, they understand solid objects, and their parents don't start telling them about these things, right? They just observe, interact with the world, and so on, and build the right abstract concepts in a way that's pre-linguistic and that's intuitive. So that's something we need to figure out. Also, if you look at the kinds of errors that current systems make, when they make errors, and they do, they are very different from the kinds of errors that humans make. In fact, often they seem to indicate that those systems rely on fairly simple clues about the input, like let's say classifying an image of a cow using the color of the background. So often it's going to be green because pictures of cows tend to be on green pastures. But if they suddenly see a cow in a beach, then they might not recognize the cow. And this is actually the kind of mistake that happens.